I'm glad you got it. So good. Okay. Any other questions on that? I mean, synthetic division, you really don't have to do, because you can always do polynomial long division, but you have to do polynomial long division if your divisor is not x minus something. Although sometimes, as you'll see, you can manipulate the divisor to get in the form of x minus something, but not always. Okay. But any other questions, though? Well, let's keep going then. Let's make this bigger. So here's another example. Now notice that we do have a dividend, capital F, right? Which I'm calling it capital F, right? So we have this here. And we're dividing it by x plus 5. Now remember, with synthetic division, it was x, it had to be x minus a number. Here we have x plus a number, okay? X plus a number. So what can we do? Well, as illustrated here, we can rewrite x plus something as x minus the negative. It has to be minus. That's just how synthetic division is set up. Always has to be minus. Okay? All right. So what we can do then is write this as x minus a number, okay? And we have -5 here, right? X minus -5. The coefficients, again, each coefficient gets its own column. So we have 1 x cubed, that's a 1. 9x squared, we have the 9 here. 23x, that goes here. 15 goes here, as you can see. So we have all this now, okay? Again, there's no missing terms here, right? You have x cubed, x squared, x, constant term. So we don't have to use 0 as a placeholder. Okay. So the 1, right, we're going to bring down, as you can see here. 1 comes down. And now we do -5 times 1, right? So the 1 we brought down, -5 times 1, well, that's -5, so that would go here, as you can see. Okay, so next, we're going to add 9 and -5. And what do we get? We get 4. Okay. We get 4. Okay, that's good. Now we repeat the process. -5 times 4, that's -20. That goes up here, as in this slide, as you can see. Okay. And then we can add to get 3. Right? We add. Good. Okay. So again, what did we do? We did -5 times 4, that's -20. We do 23 plus -20, that's 3. And we do the process again. -5 times 3 is -15. That's going to go here. Or in this case here. So we add and we get our remainder, which in this case is 0. And again, this is why we stop, because there's nothing after this. So this is what we have. So the remainder here is 0, as you can see, right? That's what the last number is. These numbers are the coefficients of the quotient. And since the dividend was cubed, degree 3, excuse me, this is degree 2, the quotient. So we get x squared plus 4x plus 3. Okay, that's good. All right. Now, and then again, using our division algorithm, we can write we can write the dividend as the divisor times the quotient plus the remainder. And it was really x plus 5. It was, well, we used x minus -5. So that's what we got. That's good. So we have this all together. Now, notice the remainder here is 0, as I said. Okay? So we know the remainder is 0. What if we did the dividend at capital F at -5? If you were to evaluate it at -5, what you will get is this. You get -5 cubed plus 9 times -5 squared plus 23 times -5 plus 15. You know, we're just evaluating it at -5. Doing so, okay, we end up getting 0, which is equal to the remainder here. Well, that's no coincidence. There's actually something more general happening, namely what we call the remainder theorem. Okay, this is the slide, but let me get to the next set of notes. Okay, let me close this. Here we go. Okay, good, good. So, you know, again, this is what we actually have here is what's called the remainder theorem. And that basically justifies what we just saw. It says that what we just saw will always happen. Namely, the remainder theorem is this. If you have a polynomial, capital F of x, okay? Now, if you were to divide it by x minus a, excuse me, if you were to divide it by x minus a, okay, then the remainder, capital R of x, okay, then the remainder, capital R of x, it turns out to be this constant, f of a. It turns out it has to equal that. Okay? So we actually know what the remainder is. It's the dividend, the polynomial, the original one, the one you started out with, evaluated at a. That's what's happening here. Now, so as an example, if we were to divide this polynomial by x minus 3, I think we did that already, and we got -4 as the remainder, right? Well, in fact, you can get the remainder using this theorem easily. You just evaluate this at -3, and that's, excuse me, at 3, and that's what we're doing. At 3, you evaluate it, you get -4, which is what the remainder was. You know, again, I think we did that example already, so no coincidence. Okay? Good. All right. Good, good. So that's one example. Well, that's actually the remainder theorem. And hopefully it's not that, it's really not hard to see why it's true. I actually have an outline of a proof here. Wait, let me just, I don't like that. Should be, I mean, it's not, that's just right like that. There, now I feel better. Okay. So basically, we're going to let a be any number, okay? A is a constant. Now, if we were to divide capital F of x, right, by x minus a, let's say we divided that. So the divisor here is x minus a. Well, excuse me, by the division algorithm, okay, by the division algorithm, what we would get is f of x is equal to x minus a times q of x. Q of x is another polynomial, plus r of x here. R of x is either going to be 0, you know, it's identically 0, or its degree is less than 1. Well, the only polynomials that have degree less than 1 are non-zero constants. 0 is a constant, so here R of x has to be a constant, is what we're saying. So I don't know what that constant is, so I'm going to call it C. So again, it's just the division algorithm. We get this. Capital R of x here has to be a constant. That's what ends up happening. So I'm calling that constant C, little c here. So substituting, we get this. Okay, that's good. But now, can we figure out what that C is? Well, we actually can, as the next line shows you. Namely, we have capital F evaluated A. So I'm replacing X by A here. As you can see, this part goes away. I mean, Q of A might be 0, but doesn't have to be. And we get plus C, which is 0 plus C, which is just C. So F of A must be C. C is F of A. Now, why is that good? Well, that tells us that C, that constant, is F of A, and so we have this. So this is why the remainder theorem is true. That's why.